as a company, we do a lot of high performance tunings and stuff in Cosmos-sdk / Cometbft. And, I'm just going to share all our findings, part of our findings that we sort of, found out as we went and how we sort of made what we have today. So a little bit of life story, because I think this is going to picture a better understanding in your head where I'm coming from, like why I'm going to talk about what I'm talking about and stuff like that. So I did a lot of like commercial sort of memory allocator stuff, like high performance stuff, because I used to write a lot of like embedded C stuff for LTE 5G scheduler. So not your phone side, but then the other like base station side. So we're talking about one CPU with 500 megabytes of memory to concurrently allocate, resources for 600 people and stuff like that. It's real time, really crazy stuff. And as a part of that experience, I like sort of had to write a lot of low level stuff, which I sort of find enjoyable, and I try to sort of apply those practices in Cosmos-sdk in general, hence the high performance RPC. And I also manage the public RPC for Terra. I don't know if you know, but I have this internal metric where at peak, i.e. on the day of collapse, we had about 2 million requests per second on ingressing into the RPC stack. So what I'm going to talk about is actually performant. And sort of moved on to found Newmetric. We're still in beta, but if you want to use it, you can sort of sign up today and start using it. We want to sort of bring the same level of RPC performance to all the other Cosmos chains. Today, we have support for about 24 chains, so you can sign up and start using the little cute secret tool called Cradle. So it lets you fork running mainnet into a dedicated testnet while preserving all the states and even the validator set. So if you want to try it out, just let me know. So naturally, I'm drawn to this like rabbit hole of performance and stuff. Like I don't just add 1 or 2 lines of code and then call it high performance. I actually like to sort of redo the whole thing, and in doing so, I have no shame in writing like widely unsafe code, which sort of kind of helped us to be where we are today. Like I'm just talking about it. So naturally, this talk is going to be like performance in Comet / Cosmos-sdk. We have found like so many foot guns in the stack in general, but obviously time is limited. So it's going to be sort of confined to the areas that I find the most interesting, RPC. And I hope that the findings here is probably generally applicable to your application as well. And it's not going to be about parallel TXs. I don't know how to do that. So yeah. This is what we have today. So like comparing to like usual RPC stack, which most of us do, is like run full nodes, probably many of them. We don't do that. We actually do sort of split what is in a full node, say the HTTP stack and state machine and database. We sort of separate them all apart, and then have a like individually scaled like set of edge nodes. This is you can think of it as like a read-only node. So it's a type of node that only does read. So it only handles like incoming RPC requests, i.e. like somebody trying to read bank balance and stuff like that. And the good thing about that is it's stateless. So it doesn't have its own database attached to it. Rather, we sort of maintain a master DB, like remote DB, and then all of these nodes sort of connect to that one node. So when I say stateless, it's like you can scale these nodes like in 10 seconds, for example. Like if the load is like, piling up too much, you can sort of, we can sort of like scale them out individually. And then we also have a separate stack for indexer, like the Cometbft TX indexer, plus we have our custom indexer too. So we also have them sort of set up individually scalable. Also, we have a separate stack just for Cometbft P2P. So we usually maintain like two different set of P2Ps. The first for sync. This is for doing the block sync reactor and then consensus reactor. So it's about ingressing the block. So what votes are being made in the network. So we know as soon as possible, okay, this is a block we need to process. And then once we have that, we sort of dunk everything to this writer node, which is sort of, kind of the closest version of full node, where it takes in a block, processes all transactions, and then sort of stores all the resulting state to our master database. So it's like kind of a Web2-esque infra setup for Cosmos, and then we tend to do that for all the other chains we support. So before we sort of dive deep in, we gotta sort of talk about how our chains work, like Cosmos chain. So this is a drastically simplified version of what a full node does. So user-centered transaction, and then either through P2P or through the RPC itself, the node sort of tries to store them in what we call mempool, right? So mempool, before inserting the transaction in the mempool, node runs checktx. So checktx results depending on its output. If it's okay, the transaction is part of mempool. If it's not, then we reject it, and then let the user know that, hey, there's something wrong with the transaction. And then so over time, before the consensus timeout, mempool would grow, and then there's some proposer in the network tries to sort of group them together or order them together into a block, and that's the part where we start calling ABCI lifecycle. So begin blocker is like a handler that gets run at every single block. So before running any transactions, we run begin blocker. And then there's deliver transactions, okay? Run transactions, and then there's end blocker, in which we usually update validators and stuff, and then go to commit. Commit is like calling IVL and storing commitments and stuff like that, and then go back to step one. So this is the usual lifecycle. Problem is, in between any of these lifecycle functions, user might send something RPC, like try to read a user balance or give me all the delegations made to a validator, stuff like that. The point at which those RPC calls are being made is in between any of these, and then I just simplify the entire AVCI lifecycle as if it's one function, but in reality, like in between of any of them, like RPC can happen, and basically a node's job is to do all this as well as handling RPC at the same time. But then all ABCI calls have locks in place. So even checktx has a lock, and a query, this is the path where, whenever there's RPC call, this function gets called. So if you look at the code, it's like sort of mutually excluding already. So like not every single call into the application is basically mutex. So that means if your query is going to this is what's happening. So there's like near zero concurrency in the entire stack, where nothing is processed in parallel. So that means if your RPC call into whatever takes 10 seconds, the node is basically locked out for 10 seconds. Like that's a problem, because some chains are running consensus clock like too fast. Like Injective's case, like 800 milliseconds. What's gonna happen to your node is probably going to be problematic, because it's going to force your node into sort of being behind compared to all the other networks. So that's what I wanted to fix in the first place. So and because of this reason, it's probably not going to scale. I mean, I know some of us like to set up a full node in a really beefy machine where like 16 cores and 60 gigabytes of memory. It's not really exactly going to utilize most of those resources just because of the locks. So we tend to just scale things horizontally, but then in resource perspective, that's sort of inefficient. Hence our architecture you saw before. So like my question was like, should it be like that though? Because like if you think about it, read workload, i.e. RPC, all it does is, okay, there's some HTTP server, user makes a request, that request ends up in state machine, and state machine sort of figures out what records to pull from the database, and then encode it, serialize it in whatever way, and then give back to the user, like why there should be any locks in between. Whereas for the write workload, the ABCI lifecycle that we just went through, it, run this transaction and store resulting state in database. So there's ideally like shouldn't be any contention between read and write, but it is the case today. So why is that? So, I mean, so if you think like intuitively, I think, some sort of data safety will be the important topic here. So making sure the read doesn't sort of bleed into the state commitments that's being made just now, controlling between those things probably would be important, but I don't know what's happening. So our goal was to make read workloads concurrent plus individually scalable, just like the structure we had before, like remove all mutexes basically. So everything is actually concurrent, and then you sort of get to control versions explicitly. So whenever a request is made to RPC, hey, this RPC's made it, height 1 million. Then we sort of log the result or resolve the database records for that specific RPC request, locked it to a certain height, explicitly controlling it. So remote database, blah, 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 blah. So basically separating all these is what we wanted to do. This is our roughly our structure. So we have, like I said, separate sync P2P, write node, and then many read nodes. So all synchronized through one single database. This is sort of the way we do it today. Removing mutexes, how you do it. You basically, why we need mutexes, like I said, potentially in any part of your application, in your keep or whatever, you try to read a record from, at a point in time, and then some code part later, you might want to like read something from database, and then between these steps, there might be some new states, kicking in, and you don't want that, right? So you kind of need to tell explicitly to the database, hey, only resolve states at a certain version. So we know that safely, all the states are locked to a certain version, and this is how we do it. So, okay, whenever something is run, we get the latest known version, and then we call database with that specific version, right? Okay. So it's not like in the database, give me whatever. It's like telling the database, hey, please only give up to this height, and then just go on with queries or writing transactions, everything. So it'll be safe in terms of version control. Stateless, but with range cache overlay. So like I said, we are using a remote database. So naturally, every single call will hit the database remotely. So TCP, whatever latency, it probably will get a little ugly over time. So what we had to do was sort of make a database cache on in each and every edge node, so that whenever a data or a range of data is pulled to that in-memory database, it is sort of cached there. And then any subsequent reads into the same sort of range or the single key isn't re-triggering like remote read. So that way we can sort of reduce the latency to almost nothing. This is not as easy as it sounds, because like we tend to use something like LRU or B-tree for memory cache, but then LRUs usually have mutexes, so it sort of defeats our purpose. B-tree, it's sort of hard to control, like how big the memory the memory consumption gets over time. So we had to find a way to keep the memory usage limited, as well as achieving the same performance. So we have that in place, almost exactly the same as cache multi-store, but we just hacked the things together in a way so we have more granular control, range invalidation. So this is like saying, okay, writer node committed these states, and this specific key, which is a member of this bigger group, is now invalidated. So, hey, edge node, the RPC node, invalidated those ranges in your memory cache, so you can sort of proceed to read from the memory database. So that's why we did it. We tend to run things in like really small environments, like I'm saying 1 CPU, 2 gigabytes of memory per read node. So when there's like pretty much no usage, it's like pretty small, and then as the usage grows, it's sort of scaled linearly. Probably gonna skip that part. So what is it like? So injective, this is injective's case. So this is a vanilla node, one full node in 16 core, 60 gigabytes of machine. It can do about 500 to 600 requests per second. In our node, it can do about 10 times a bit more with one replica. while also achieving the P95 percentile pretty controlled. So P95 in this vanilla node is like shoot up to like a second. In that case, it's like down to 100 milliseconds. It's fast. We're also doing like public RPC for Initial testnet now. This is day one metric, so 140K ops per second without cache. That's, I think, pretty impressive. So we do that. P90, 26 milliseconds. P99, some queries are heavy, so it sort of shoot up, but in general, it's pretty fast. So that's what we have. Probably not as important as the others. So I'm running out of time. So, yeah, we actually do concurrent check TXs as well. So all the check TXs are like sharded using signer info. If you have a question about it, just let me know. Yeah, that's the end result. So it's fast. All right, so that's it. Sorry for the word vomit. Let me know if you have questions, and any discussions further. Let me know. All right, thank you.
Hey, that's it.
There's one.
Just how much of this are you willing to upstream into the SDK?
We cannot. It's at this point we have changed more things than what is left from the original upstream. So, we hope, but I think we're gonna introduce this as an SDK that's sort of superset of the existing Cosmos SDK. So if you want to use it, you can sort of keep the existing modules, but then sort of import into whatever SDK we provide. Yeah.
But aren't you then in a race where you're trying to maintain feature parity ongoing?
Maybe, but the way we structured it is we don't know what exactly is happening down in the Cosmos SDK layer. So it's crazy, but we take in the types, so we know how to deal with the types like blocks. What is a TX? What is a specific proto? But we kind of redid the entire lifecycle. So as long as there's a type integrity, it probably wouldn't matter too much. Yeah.
And everything is like state compatible with the node that's running.
Yeah. Well, we try to make that. Yeah. It is today. So yeah. Yeah. Yeah, I guess it's a little, probably very pedantic level of technical stuff, but yeah. Hello.
So can the P2P work that you guys are working on,
Yeah.
Can that be kind of integrated into the existing stack, or is that also?
It is. I'd say it's compatible, but we sort of gave up on upstreaming this to Comet, like the same question, but because we basically redid the entire reactor pattern. It's not Cometbft. It's just exchange the same type of messages, but it's like different enough to call it a different software at this point. Yeah. Yeah. Any more questions? Hello.
What are the high level? Is there any
Drawbacks. So obviously the biggest drawback will be so some applications tend to bake in their own custom feature in, say, Comet multi-store. Like, for example, DYDX mainnet v5 added one little, more method to the Comet multi-store, which we would have to manually patch things out for now. But we hope that we kind of find a way to not care about any of those and then, automatically do stuff. Also, because it's like remote database situation, if the read span, for example, like TX indexer from Cometbft tends to have a really ugly memory consumption overall. So depending on the query pattern, it may actually panic due to the memory consumption. So that's something we're trying to fix still, but yeah. Any more questions? I think, yeah.
Why not Avita?
Stone. I've been saying that for past year, but yeah. Yeah. All right. I think that's it. Thank you.